Okay, so I wanted to take, we wrote down some formulas for the entropy, and I mentioned this issue that when it comes to gravity, quantum gravity in particular, we don't have a once and for all answer to what the entropy is. So, but nevertheless, there's special circumstances in which we understand the entropy well enough that we can make some statements about what the entropy of the universe was that are at least a little bit reliable. So let me draw a picture of what many cosmologists think of as the conventional history of the universe. We start with inflation. And inflation happens, and then you get some reheating. And reheat. And the universe expands, and it gets to where we are today. Oh, terrible. Okay. So here's the future. Here we are today. And I claim that I know well enough what the entropy is, or at least, more or less what the entropy is, because the sizes of these numbers are so ginormous that the details actually don't matter. So actually, if this is the CMD, or reheating, it doesn't matter, even though there's a big difference in scale factor between reheating after inflation and the CMD. There's not a big difference in entropy. So, because basically at that time, the universe is just a box of gas. It's just gas spread out more or less uniformly with the temperature, except for the fact that the universe is expanding, and except for the fact that there's not been anywhere near enough time for gravitational structures to form. Locally, the gas looks more or less like gas in thermal equilibrium, and we know what the entropy for that is. So for a thermal bath, the entropy has a formula. I should probably use tilde signs here, even if I get the right answer. Rho plus P over T times V. Energy density plus pressure divided by temperature times the volume. What do I mean by the volume? I mean the co-moving volume that is similar to our universe today. So the universe is expanding, but I can sort of take a region a few tens of billions of light years in radius around us, and I can expand or contract that upward and downward with the universe. It's not quite a closed system, but because the universe is homogeneous, it's pretty much similar to a closed system. If you literally put a wall around that co-moving volume, what happened inside and outside the wall would really not change that much. So that gives me a volume. I know the temperature. I plug it in. The answer is about 10 to the 88. So that is the entropy here. Or our co-moving volume today at the era where there was a gas that was hot and dense, but there were no structures gravitationally formed. Now, once the structures begin to form, it's much harder to get a once and for all formula for the entropy, but we had a formula for the entropy of a black hole. The entropy of a black hole is, how do I put it here? In convenient astronomical units, astrophysical units, 10 to the 90th times the mass of the black hole over 1,000,000 solar masses squared. So 1,000,000 solar masses is chosen because many spiral galaxies have supermassive black holes at the center with masses of order 1,000,000 solar masses. In fact, they can go up to something like 1,000,000,000 solar masses. But the point is that even our galaxy all by itself, just the one black hole in our galaxy, which is something like 4 or 5 million solar masses, has more entropy, 10 to the 90th, than every photon and neutrino and dark matter particle and baryon, etc., in the whole universe. So this is a reminder of how low entropy the universe is. You say, well, you're full of all these photons and so forth. It looks almost like thermal equilibrium. It looks high entropy. You just make one little 1,000,000 solar mass black hole, and that is more entropy than the whole rest of the observable universe. And you add these up, and you get the best estimate that I could find recently is about 10 to the 103. So you add up all the black holes in the known universe, you figure out their entropy, you add them up. So that is the entropy today, 10 to the 103. Happily, it is larger than 10 to the 88, because the second law of thermodynamics is still true. Now, what will happen in the future? Well, in the future, the universe is expanding. We think that, well, it's accelerating as well as expanding. The current observations seem to be compatible with the idea that that acceleration is caused by an absolutely constant cosmological constant. So it could be slowly varying quintessence or modified gravity or something like that. But the smart money at even odds would be that the acceleration is really just caused by a cosmological constant. It's a small number that's making the universe accelerate. And what will therefore happen in the future is what Fred was telling us about. You know, the stars will burn for a long time, as it were, but eventually they will give up. About a Google years from now, 10 to the 100 years from now, the stars will have died out, the black holes will have basically evaporated, and we'll be left with nothing but empty space. So, part of you wants to say, well, empty space is just...
Empty space filled with photons, electrons, positrons, and neutrinos.
No, empty space, because there will be less than one of those per horizon volume. Because we're waiting a long time. Everything expands away. Everything, all the density goes to zero. If there are 2 protons in your horizon volume, then just wait another e-folding, and then it'll be less than. Eventually, it'll be empty. So you're tempted to say that's a unique state. You're in the vacuum state. But that's what you were talking about before. You can attach an entropy to de Sitter space. Now, I have to violate my own stated rule of talking about the co-moving volume, because the co-moving volume of our universe today is approximately equal to the horizon volume. And I already told you by complementarity I'm not allowed to talk about multiple horizon volumes. But I can still put a horizon volume sized circle around myself and say that in that patch, the de Sitter entropy S, given that formula right there, is 10 to the 122. So the entropy up here is something is at least 10 to the 122, depending on whether you want to count things outside our horizon. Just inside our horizon, it would be that. So again, going up, that's good. And also remember, the entropy is the logarithm of the number of states with this macroscopic form. So an increase from 10 to the 103 to 10 to the 122 is an increase of a number of states of the form e to the 10 to the 103 to e to the 10 to the 122. So compared to e to the 10 to the 122, e to the 10 to the 103 is approximately 1. It's nothing. The entropy of the universe today is very, 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 very low compared to what it could be. So if you go back to inflation, again, we are in a situation where we don't have a once and for all formula. Yeah?
So this seems like a little bit of a sleight of hand, because...
Little.
Fair enough. So it's not clear that there's a way to interpret the horizon entropy as entropy on the inside of the horizon. It could also be interpreted as ignorance of what lies beyond the horizon. So when you're putting the black hole entropy and the CMB entropy on the same footing as the horizon entropy, it sort of begs the question.
I think that is fair, but I think that, certainly it's fair to the extent that I'm not utterly justified on the basis of understood physics in saying this. I would argue that if I take the horizon and what's inside as the physical system, the most straightforward interpretation of this is that the entropy of that is this formula. Whether or not it should be thought of as holographically living on the boundary or all in the bulk, maybe there's some duality between those two possibilities, but I kind of don't care. I'm just saying that at least this part of the system is properly described with that entropy.
Well, if you were doing that, then the entropy today would also include the horizon entropy.
Yeah, so that's very fair. But it could. Let me get this right. Because that is not de Sitter space or a black hole or anything like that, we have less understanding and less control over that situation. Nevertheless, I think it is fair to say there's sort of a first guess as to what to do. The horizon is smaller because they matter in the universe, so it shrinks a little bit. So it would still be true that the entropy today would be substantially less than it ultimately relaxes to. But it would be bigger than that. Yes?
I just wanted to remind people that Lenny Susskind last week tried to give us a physical interpretation of this entropy as arising from basically entanglement between the particles outside and the particles inside, and it works equally well if you're talking about an event horizon around a black hole, which is the case he talked about explicitly. But he used the Rindler argument, which is basically the Unruh argument. So it works equally well for the event horizon that surrounds us. So it's real entropy, and it has a simple interpretation, and in fact you can do a string theory calculation and calculate the number of states, and it actually comes out to be what this tells you.
I think so, yeah. So those are among the reasons why I think this is valid. I'm just, I think it's legitimate to be careful in saying that as good as these arguments are, it's not like we've experimentally tested them. So, it's all very, very reasonable stuff, which is beyond what we really claim to be under our control. Yeah?
Just for clarification though, if you want to include the horizon entropy in the entropy budget, why wouldn't you be doing it in the past and today as well as in the infinite future?
Yeah, so I think that that's a perfectly valid thing to want to do, but I don't have control over it. It would still give me the same moral of the story, and it would still be going up, but maybe that is the right thing to do. I'm not saying that's wrong. Anything else? Well, sorry.
Actually, there is a time issue that we sort of, in all of these discussions, except Lenny, who was a little more careful about it, of Higgs, and that is, so when exactly does a black hole form? And from the outside, it never forms, never finishes.
Yeah.
And so the same presumably applies also to the de Sitter horizon. So the question is, at what time is it appropriate, from our point of view, outside the black hole and inside the de Sitter horizon, to ascribe this entropy to those objects?
Yeah, I think that's
and I've never
right.
actually gotten a clear answer to that question.
Well, that's similar to what I was just going to say. I think that I could give a stronger answer to your objection, which is that if I'm counting the co-moving volume here for every moment earlier than today, including, in fact, today, but only for a little while longer, the co-moving volume is smaller than the horizon volume. So I think I could make an argument that I shouldn't include the entropy associated with the horizon volume in the co-moving.
Are you talking about the co-moving volume that's the same size as our particle horizon today?
Yeah.
Because, well, right now the particle horizon is bigger than the event horizon.
Well, these are factors of order unity. I mean, so it was much smaller back then.
Yeah, it was in the early universe that was inverted. So
That's right. And during inflation, so inflation has this remarkable property. I mean, there's a lot of, I'll give a little bit of an anti-inflation spiel, but I like inflation. I think inflation is ultimately going to be right. I think we misrepresent it sometimes. One of the hidden virtues of inflation is that it makes it easier to imagine what would eventually be your theory of initial conditions. Inflation is sometimes said to remove the need for a theory of initial conditions, but I think is totally false. But at least it changes what kinds of initial conditions you need. Instead of needing a Robertson-Walker universe with 10 to the 88th particles and a co-moving volume, you just need a little Planck scale or slightly larger gut scale size thing, which is in the false vacuum. Yes?
Could you maybe more precise your statement when you say that it's false that inflation should solve the initial conditions? Why do you think what's the motivation for inflation?
Well, don't worry.
I'm really interested.
I know, but I have that for the next hour and a half. I'm going to be talking about that.
Okay.
That's why we're here. Yes. So I'm just trying to, before I start criticizing inflation, I'm saying there's one thing that it does very well. If you take our universe, our co-moving volume today, and you didn't believe in inflation, and you just thought it was a radiation-dominated universe that you extrapolate toward the past, at the time when the density and the Hubble constant reached the Planck scale, the energy density was E Planck to the fourth, and the Hubble constant was the Planck mass. At that time, our co-moving volume would have been about 1 centimeter across, 10 to the 88th particles. Now, that sounds small when you compare it to like 100 billion galaxies, etc. But what you're saying is that you need to fit those 10 to the 88 particles into not, you need to distribute them over a cubic centimeter, which is huge compared to particle physics scale. So the expansion rate is the Planck scale, but the physical size is a centimeter. So it's many, many, many Planck volumes in that universe. And it's the same conditions everywhere, in every single one of those Planck volumes. That is part of this fine-tuning of that you need to explain if you don't have inflation. Whereas if you have inflation, because you can inflate, you could actually imagine starting the universe in a much, much smaller volume than 1 cubic centimeter. Now, the entropy in that volume, I'm going to cut short the discussion because I have more interesting things to talk about, but the entropy in that volume is close to 0 in that proto-inflationary state. You're pretty close to the vacuum state. You have some sort of de Sitter entropy, but it's, let's say, of order between 1 and 10 to the 12. Something like that, if you just go through how big might the volume be, what might the temperature be, what's its de Sitter entropy, and so forth. Yes?
So, on this way of looking at things, it's not that inflation would explain this low entropy state, rather it would presuppose it.
Absolutely,
And you
yeah.
can arrive there. I see.
Again, we're going to talk about this stuff. But right now, I just want to get on the board that inflation starts in a very, very low entropy state. If all you're doing is counting how many states you have to choose, inflation is a very, very, very precise arrangement of stuff. That's the bad news. But the good news is it's a very small arrangement of stuff. If you had a theory of universes be created from nothing, or as quantum fluctuations, or something like that, the volume might actually matter to you, and inflation wins on that score, if nothing else. Okay. So this is kind of what we want to explain. Why did the universe start with such a low entropy? Either 10 to the 88, which is still much smaller than today, or maybe 10 to the 10 or something like that. I should also say there's another problem in this whole discussion, in that the only language we really have to talk about these things is this quantum field theory language. But there's got to be something that goes dramatically wrong about quantum field theory along the way here. If you believe in inflation, just as an example, if you believe in inflation, take a CMB photon today with a millimeter wavelength, millimeter order of magnitude, and you blue shift it backwards in time to the beginning of inflation, the wavelength of that CMB photon is much, much shorter than the Planck length. So you assume that that mode of the quantum field is in its vacuum state, and you have to do that for every single possible mode of every single field that is in the universe today. But if you think about counting degrees of freedom, you just dramatically failed. If you only count quantum field theory degrees of freedom, the degrees of freedom seem to increase with time because you have more volume if you just take the co-moving horizon size and divide it by the Planck length. That's a time-dependent quantity. But the degrees of freedom shouldn't change, the number of degrees of freedom, because that's not compatible with unitary evolution. So if you believe in unitary evolution, then you have to believe that the fraction of the quantum states that are accurately described by quantum field theory changes with time. And that over here, in early times, only a tiny number of the possible accessible states were actually describable by QFT. Yes?
But I take it the quantum theory we're expecting to have is one that includes gravitation, is
Sure.
one that includes space-time degrees of freedom.
That's right, yes. So that's an obvious place to put those
Yeah.
degrees of freedom, but we
Right.
don't know what form they take.
Okay, sure, but but it's not, the point is that this doesn't seem like prima facie reason to believe. I don't know exactly what you meant by QFT, but if you meant representation of possible states by Hilbert space, or if you mean that prima facie this shows that the number of fundamental degrees of freedom can't be constant, including the spatiotemporal degrees of freedom, it's not obvious that it shows something like that.
No, I mean the opposite of that. I mean, so I'm buying, I'm admitting that I'm assuming from the start that the space of states is fixed.
Right.
The number of degrees of freedom does not change. I'm pointing out that in a box the size of our co-moving horizon,
Sure.
the number of degrees of freedom that can be described by quantum field theory
Sure.
does change.
Sure.
So they need to change their.
But nobody thinks that's the way it's going to be. But sure, okay, good.
Just kind of focusing in more on that, and this is similar to some questions I asked last week, that just whether or not we should expect cosmology to obey unitary evolution. So if you're talking about a co-moving region the size of the particle horizon today, you might make a good argument that it's approximately a closed system, not so much matter flowing in and out. But you certainly couldn't make that argument for the cosmic event horizon. There are galaxies that are leaving the cosmic event horizon as we speak. So,
Nobody would make that argument, right?
So would it be fair to say that if you're restricted to the cosmic event horizon, you would expect to see something which looks on
Sure.
Okay, so that's perfectly reasonable.
Yeah, I mean that's a very definition of an open system. So open systems do not obey unitary equation.
So when you're talking about cosmology preserving unitarity, you must be talking about on a much, much larger scale than the cosmic event horizon.
For the whole universe, I think it would be strictly true, and for a co-moving volume, it's possible. That's the idea. Okay, so let's talk a little bit more about inflation. I know this is a hot button topic for people. I'll lay my cards on the table. Like I said, I think that inflation has a lot of good aspects. At even money, I would bet that probably inflation does play some role in what happens in the actual universe. I think that the story that modern cosmologists tell about inflation is woefully inadequate. We need to do much, much better to claim that it's on the right track, which obviously implies that it might not be on the right track. I just don't know. So you've heard about inflation before. I'm not going to give you the long spiel about it. Here's a cartoon of the potential energy, some scalar field. There's a false vacuum and there's a true vacuum. And there's a lot of details here. Sometimes they get glossed over. This can't be the final right answer because we know that you need a long stretch of slow roll inflation in addition to this kind of bubble nucleation. But when you talk about the multiverse, it becomes more convenient to talk about this bubble nucleation kind of picture. And there's a dialogue that goes back and forth. We basically had the dialogue already, but so I won't write it on the board, but I'll just sort of remind you of it. Someone says, look, the early universe, the CMB, it seems very unnatural. It seems very finely tuned. It's very, very smooth. It's very, very flat. That's a surprise. I have an explanation for why it is like that. The explanation is it began in a tiny little region of space in the false vacuum state. And that false vacuum state has the property that will expand, it will reheat, it will cool, it will smooth everything out and naturally give us this kind of CMB, this kind of early homogeneous dense state that we observe. Therefore, I have explained why the early universe apparently seems finely tuned. So the analogy for this is you're climbing up Mount Everest, and as you walk, you see that there's a bright red bowling ball sitting halfway up Mount Everest. And you say, this is very strange. How did the bowling ball get halfway up Mount Everest? And one of your Sherpas says, I have a theory for how the bowling ball got there. The bowling ball started at the top of Mount Everest and it rolled down. Well, okay, that would suffice to explain why the bowling ball is halfway up Mount Everest, but it raises a harder question, which is why there was a bowling ball at the top of Mount Everest. And that is the problem for inflation. So if you are simply trying to say that you have a natural explanation for why the universe looks like the way it did, you can phrase that by saying, I'm trying to understand why the universe was in one of such a small number of possible states compared to the number of states it could have been in. And you're saying my explanation for that is that it was in an even smaller number of possible states, and from that everything follows. So purely at the level of fine-tuning of initial conditions, it is not at all clear why inflation should be counted as an improvement over simply saying that the universe started in a hot Big Bang in a homogeneous state. So then the pro-inflation person comes back in dialogue and says, actually this takes decades, but eventually the pro-inflation person says, okay, I get it, I understand what you're saying, but don't worry, I have a solution. The solution is called eternal inflation. So you heard a little bit about eternal inflation. Again, I won't draw the full picture on the board. The point is that when you talk about like bubbles being created and percolating, you talk about that, right? So if you do think that the potential energy of some scalar field takes this form, this energy density counts as a cosmological constant, as a vacuum energy. It makes the universe accelerate. You imagine that there's a quantum probability to make a little tiny bubble which then grows at almost the speed of light. And you can say, well, there's two regimes. One is the bubbles are created so rapidly that they can bump into each other and percolate, and the whole universe makes a transition to this state down here. Or they don't. Those are the two possibilities. The problem is that if they are nucleated rapidly enough to percolate, then you don't get enough inflation. You get an order 1 expansion by a factor of E or whatever. The universe doesn't inflate for very long. It needs to stay in the inflationary regime for like E to the 60th expansion. So you want those bubbles to be nucleated very slowly, and that's why the bubble nucleation by itself doesn't actually do the job. But once that is true, if the bubbles nucleate slowly, then they never percolate. It's not that you can make them very rare, and therefore you can get a lot of inflation, and then inflation ends. If you make them rare, inflation never ends. You can make a bubble, it will expand, but it will generically not hit all the other bubbles around it. And it's exactly because of this horizon phenomenon. You make a bubble out here, it expands at the speed of light, it never hits you. You never see it. So a space-time diagram of this looks, say, if we were in here everywhere, if you call this the false vacuum and this the true vacuum. Notice that I have very intentionally put the true vacuum not quite at 0, because we have vacuum energy today. You imagine that here is the universe. If we were in the false vacuum everywhere, then the universe would just be de Sitter space. That's why I'm drawing a square. Remember, this is just my two-dimensional representation of that cylinder thick, filled-in cylinder that is the conformal diagram of de Sitter space. So you're happy with me drawing this square and saying that's de Sitter space, right? Would you like me to explain that anymore?
You're identifying the edges.
No, it's a sphere. Everything here is a three sphere, every slice. Okay? So you put yourself in a false vacuum, but then you say, I don't stay in false vacuum forever, I make bubbles. So making a bubble looks like this. A bubble is nucleated, it expands at the speed of light. The beauty of the conformal diagram is the speed of light is 45 degrees. And inside this bubble, you're in the true vacuum. Like I said, there's two choices. Either you nucleate very quickly, all the bubbles run into each other, and that would mean that down here, there's all these sorts of bubbles bumping into each other, and you complete the transition, and you find yourself in the true vacuum at the end of the day. Or it's rare that you make bubbles, and it looks more like this. And that's not exactly right because, remember, the volume here, the volume of space, is exponentially increasing as you go from here. Let's draw some initial surface. This is sigma 0. As you draw later surfaces, the volume of sigma 0 in cubic megaparsecs exponentially increases. So, and the time actually exponentially increases also. The time between two equidistant slices is longer and longer as you go up here. So in fact, there are bubbles that fill in this future boundary, but they fill in a way that if you're very, very careful about it and calculate, you realize that the physical volume in the false vacuum grows with time. You never stop inflating. There's always more and more space in the region of the false vacuum. There's also more and more space in the region of the true vacuum, but inflation never really competes. Yes?
So is it right to say that there are a number of different stories that get told about how this bubbling works, right?
No, there's a small number of stories I think that are told.
Oh, okay.
The
So
bubbling is something we pretty much understand.
okay, so this would be different from the tunneling stories that get told, or
No, this is the fate of the false vacuum. If the theory is this quantum field theory in a classical space-time background, it is understood. Coleman and DeLucia,
right? So,
1970 something.
right. Okay, good. So it's not the fighting nucleation or anything like that.
No, these are CDL bubbles.
Good, good.
Yes, Fred?
Well, as you know, you can always change the story by coupling it to another field, right? I don't know if that will affect your argument or not, but...
It will not affect my argument, because I will not let you do that for my argument.
All right, well, then I will be quiet.
This is full employment for cosmologists. You can add more fields, you can change things. Yes, that's right. I'm not going to do that. I have standards. But this theory of inflation doesn't work, so you need to do something. Okay, so one thing to do is add more fields. Another thing to do is to change the shape of that potential. There's many things you can do. Okay, so remember the pro-inflation argument was, all I need to do is start in this very simple state and I explain the universe. The anti-inflation person came along and said, yes, to get into that small state requires much more fine-tuning than just start the universe. You haven't done anything at all. The pro-inflation person comes back and says, well, as long as I start once, as long as somewhere in the amplitude of the wave function of the universe, there's some region of space that is big enough in which inflation has started, the volume of that region grows forever. The volume of inflating space-time, if you have the right potential, if you have enough to begin, no matter how unlikely it is, no matter how small the amplitude is in the wave function of the universe, you get an infinite amount of volume. And then you get an infinite number of bubbles that are created, you create an infinite number of universes. So even though it might be hard to start inflation, this argument goes, once you started it at all, you win. Because you get an infinite number of observers in the post-inflationary universe. So then the anti-inflation, this inflation skeptic comes along and says, well, wait a minute. Infinity is a very big number. It is true, you get an infinite number of bubbles, but you get an infinite number of lots of things you don't want. So you should figure out some way to calculate the number of things you want versus the number of things you don't want, for example. So maybe I should tell you, well, I'll just say it in words. There are Boltzmann ratings, for example. There are Boltzmann lecture halls, like this. In this thermal state, remember you're in de Sitter space, it has a temperature. Here's the temperature. When lambda is high, the temperature is higher. If you get an infinite volume of space with that temperature, just through thermal fluctuations, you will fluctuate into all sorts of crazy things, including copies of us here in this lecture hall with memories of seeing deer, but without any actual deer. Okay? So naively, if you just look at space-time volume, there's no reason to believe that this explains the past hypothesis. There will be an infinite number of observers in this ensemble for which the past hypothesis is not relevant. There will also be an infinite number of observers for which the past hypothesis is relevant. And so you need to compare them, and that's the cosmological measure problem. It has only a linguistic relationship to the measurement problem of quantum mechanics. It's the measure problem counting a certain number of observers versus some other number of observers. The usual way it's formulated is to say, I have events of type A or B. I would like to calculate the probability of seeing an event A divided by the probability of seeing an event B. And I do that by regularizing things. So here's sigma naught. Let me draw some later surface up here. Sigma t in the future of the universe. And there's a volume V of t, which is in between sigma naught and sigma t. So I'll try to indicate that here. This is a volume of space-time that is finite in volume. But as t goes to infinity, the volume goes to infinity. So maybe I can calculate the relative probability by taking the limit as t goes to infinity of the number of appearances of A in the volume divided by the number of appearances of B. Maybe. That would be the hope. Regularizing this infinity divided by infinity by making it a finite number divided by a finite number and taking the limit. So the problem is it clearly depends a lot on how you draw that surface, sigma t. Let's say you just draw it in the most naive way. You just sort of take this de Sitter background and you draw flat slices through it like that. That is a way of regularizing the probabilities, and you get utter disaster. For example, you get what is called the Youngness paradox. If you think about what happens as this surface sigma t goes up towards t equals infinity, you're hitting more and more bubbles. The number of bubbles that you hit in any given surface increases because the physical volume is just getting bigger and bigger and bigger without bound. In that very, very big surface, we expect to see a lot of little bubbles and a smaller number of big bubbles, because you keep creating more and more little bubbles. If you want to ask what a typical observer looks like on that slice, the typical observer is going to appear, even an observer, I should make this clear, an observer that appears after a Big Bang. So every bubble counts as a Big Bang, and there's surfaces of constant density here that are hyperbole inside the bubbles. So you say, all right, you've had a Big Bang, you're expanding, you have the past hypothesis, you've inflated, so everything is smooth, and you've reheated, so you see a universe that looks like ours. But the number of such observers, if you do the regularization this way, is exponentially favoring observers that appear as soon as they possibly can after the Big Bang. So I don't know how fast an observer can appear after the Big Bang, but it's certainly faster than 13.8 billion years. I don't see any reason why observers couldn't appear after 5 billion years, for example. Through random quantum fluctuations, they could probably appear much, much faster than that. So this way of regularizing things makes a physical prediction that is obviously false. That's why there is a cosmological measure problem. If it weren't for that, people would have been lazy and given up and said, okay, we got it right. But this way of regularizing things obviously gives us an unacceptable answer.
I'm still on check something before you even got to this particular dialogue, just the last one before. I mean, wasn't it low entropy that was meant to be motivating this move to this picture? I mean, because the answer from the anti-inflationist seemed to be something like, look, I've given you something which for a long time would occur, and it occurs, and it dominates. That sounds nice, but I didn't quite see how that's an answer to the question that was originally, oh, we have something with low entropy, giving something with low entropy and explaining that.
So let me try to do, I'm not sure I can do better than repeating it, but maybe you can pinpoint where I'm missing. So the old school argument was, how hard can it be to get a little patch of space dominated by false vacuum? And once I do that, I get everything via inflation. The slightly more sophisticated people, who include Roger Penrose, who made this argument before inflation was invented, say, well, it can be really, really hard, because you're taking the whole physical system that is our universe today, 10 to, 100 billion galaxies, etc., and putting it into a Planck-sized region in a very low entropy state, and that's very, very hard to do. And then the pro-inflationary people come along and say, okay, I understand, but if there's some quantum amplitude, no matter how small, for getting inflation to start, I get literally an infinite number of observers after that. So rather than explaining why the universe started with low entropy, they're sort of unasking that question. They're saying that, yes, it is very unlikely to start in that state, but once I start in that state, I get an infinite number of universes, an infinite number of observers.
I like to be comfortable with that. Because we moved from sort of talking to observers very quickly, and that was kind of odd as well, where it's over here, there's nothing about observers quite yet.
That's right, that's exactly right. So you can draw this space-time diagram, but then in this space-time diagram, they're taken naively, this room occurs an infinite number of times. And so to match this cosmological model onto a prediction means you have to draw a correlation. You have to say, when rooms like this appear, what should you expect to be outside? You're trying to get this cosmological realization measure. And what I'm pointing out is that the naive attempt gives you the wrong answer.
So I think one way to look at this dialectic is that, we've just sort of been redoing the question each time. So with the new physical framework comes a new way of thinking about the whole unlikely problem. So we're not, in a way we're not sort of responding to the kind of challenge there. We're saying, look, maybe think of it this way and see if you like that better.
Well, that's right. So I think that if I were to think that this is on the right track, what I would say is, no, you're right. It's not that the proto-inflationary patch was a natural starting point. That was not the right way to think about it. We were just wrong, mea culpa. However, the idea that the physical process of inflation can be part of your cosmological evolution might allow you to do better than just writing down the measure on the space of possible things that could happen in our local environment. They could actually say that cosmological trajectories have this feature that when you have an observer, it is a post-Big Bang observer. That would be the hope. So they're saying that you were asking the question in the wrong way. You're not asking for generic initial conditions. You're asking a more sophisticated question. In the whole history of the universe, what do most observers see? I think, you were first.
Yeah, so just a quick question of clarification and then a worry. So just to go back to the bubbling, just so it's right in my own mind. So you hinted at this, I don't know how much this is related to the CDL bubbling mechanism. You hinted at how you can get these sorts of universes situated embedded in this background space-time by means of thermal fluctuations. Is that a part of the CDL story, or is that sort of like a different, something you could get?
It's not directly part of that.
Okay,
It's just
okay.
thermal fluctuations
Cool.
in this
So
background.
that's kind of my head, thank you.
That's right.
And then the second quick thing was just this. You might wonder if the anti-inflationists would just say, look, there's this, we want to do some particular experimental work with a particular theory. And it seems really strange now that this theory is invoking an infinite amount of universes situated in this background base of space-time, which has its own infinities. And it's just like this explanation is becoming really, really bloated.
Very fair.
Its ontology recommended is becoming extremely bloated. Just wondering if that's a
Well, I think, again, to be fair, it is true that it seems like a very complicated story to tell. Or at least a story that involves a lot of stuff other than our observable universe. But to be fair, I don't think that you should. I don't think the measure on ontologies is given by the amount of stuff. I think it's given by the amount of sort of the conceptual framework. This is actually really simple. This whole picture is this plus a couple of equations. This is a prediction of a very, very simple theory. Yes, the realization of a specific semi-classical universe looks complicated, but the ontology is as simple as can be.
So you're saying there's a kind of theoretical simplicity here.
That's right.
It might generate a kind of bloated ontology insofar as what you mean by that is a lot of entities, but don't understand simplicity that way. Understand it in terms of theoretical simplicity. Okay.
So I just want to understand a little bit better what the concern is that gives rise to the whole picture in the first place. So the thought is that if I have good reasons to believe a theory that says that the vast majority of rooms like this don't have deer outside, then I ought to expect when I look outside to see wild chaos or something like that, and that's not what I see. But I want to understand a little bit better exactly how that argument goes. So once again, I say to myself, gee, I got the following problem. I have good reason to believe in these microphysical laws. These microphysical laws predict that the vast majority of rooms like this don't have deer outside. But I look outside and I see deer, so I've got a problem. But look, if I imagined myself in one of the rooms, if I play the game of distributing the possibilities of where I might be over all the rooms that look internally like this, I'm distributing myself over a set of rooms in the vast majority of which the people don't have good reason to believe that this is the theory. Because of the reasons you cited at the outset. At the outset of your first lecture, that is what you call the cognitive instability, or what you said I called it.
That's a measure-dependent statement you just made.
What's that?
That's a measure-dependent statement that you just made.
No. Listen, I'm supposing the worst case.
Yeah, okay, right.
Take the worst case, okay?
Yes.
The worst case is the vast majority of rooms like that, are rooms in which outside there's chaos, okay? You seem to be saying, look, that's a problem, because what a view of the world like that predicts, okay, is that if I look outside this room, I shouldn't see deer. And I look outside the room and I do see deer, okay?
No,
but I don't understand how the argument that that's what I should see goes.
I tried to be better than that. I tried to just quote you when I said that the argument against it is cognitive instability. If that is the measure I should be using, then I have no right to believe anything about the world.
No, but wait, now I don't get it. If that's, suppose that's the measure, I don't know what you mean by the measure you should be using. Suppose by some reasonable measure, there are many more rooms now, or there are many more rooms in total, or whatever the relevant thing is. There are many more situations I could be in, which are cognitively unstable.
Right.
Okay. Good. I see that that's the situation of the world. Okay. That is, I see that I have good reason to believe that that's the situation of the world. And I say, what kind of judgment should I make as to the probability that I'm one of those cognitively unstable guys? Well, the minute I even entertain the possibility that I'm one of those cognitively unstable guys, my reasons for believing that those guys exist in the first place go away.
Right.
So what if somebody were to say, what I ought to do is distribute my probabilities, not over the set of rooms that are like this one, but the set of rooms in which I could rationally entertain the possibility that I am in. That would throw out all the guys with cognitive instability. So it wouldn't predict that when I look outside, I'm unlikely to see deer.
Right. Good. So so that is equivalent to saying that when there are many macroscopically indistinguishable examples of rooms like this, in this ensemble, some of them might be in local environments which are cognitively stable, and many more might not be.
Right.
And what is to stop me from, before I actually look outside, putting my own measure on there that does not come from physics, but comes from epistemology, which says that I put very, very high credence on me being in a room that is in a cognitively stable environment.
No, it's a little more than that. It's worrying that to do otherwise would involve some kind of incoherence.
Well,
you're describing it as if it's a
there's
choice.
a third option, which is to say that that's not the right cosmology.
No, sure. But I mean, suppose somebody tells you, presumably we don't have any good reason not to believe this. Suppose somebody says, you know what, I bet, this is a sociological prediction. In the far future, there are going to be a lot of mad scientists around, they'll have a lot of money. Just for fun, they're going to make a lot of Boltzmann brains. Okay? A lot of them will be by chance in your mental state. Do you think that gives us reason so we make this prediction now, okay? Do you think that gives us reason to think that if we started doing experiments we get other than the results we expect?
Okay, I think this is, I'll make two statements,
Right.
and then we gotta go on.
Okay.
Because I think this is a very good set of questions you're raising here. The first statement is to actually answer that question that you just asked. I think that given some clearly delineated notion of what it means for the brains to be in the same mental state, which might involve some environment for the brains, etc., I think the answer is yes. I think that you should give equal credence to every one of those appearances.
Okay.
And the second statement, more importantly,
Do you want to say a little bit about why you think that?
I think that's what.
You know what? Let me just ask the question in a slightly different way, and then I'll shut up.
Okay.
Okay.
I'm making predictions about it.
Here's a claim. Okay. Or here's an observation. I wonder how this observation affects the way you think it's reasonable to distribute your credence. Consider the following sequence of steps of reasoning. I run around, I do experiments. Okay? On the basis of these experiments, I become convinced of a certain microphysical theory. I see that it's a consequence of this microphysical theory that most rooms, like the one I see around me, are Boltzmann rooms. I conclude that that since I have good reason to believe this theory, I have good reason to put high credence in my being in a Boltzmann room. This is incoherent.
Right.
This sequence of reasoning.
Yes.
Okay? You can't get there without contradicting your first premise.
That's right.
Okay? That you had good reason to believe that. Why don't considerations like that give you pause about distributing your credence in the way you're suggesting?
Because I don't think you have a choice. I think that given the cosmological model, given the theory of the universe, there will only be one right way to distribute your credences. And I think that if you're in environments which are truly indistinguishable from each other, then giving them equal credence is the only way to go. And I think I'm not justifying that statement, but you asked me for my belief, and that is
Yeah,
my belief.
but you're not even responding to that. Okay.
My other statement I wanted to make was that in this actual cosmological scenario, it is true that, okay, there's people who are in post-Big Bang, ordinary observer, cognitively stable environments. There are other people who are Boltzmann brains. You might say, well, maybe I can just say that I'm in one of the ordinary observers. But for every ordinary observer, there's a huge number of almost ordinary observers. Observers for which the entropy has increased for the last billion years, but before then it was higher.
Right.
And I just see no reason, I don't see why in the world I would be able to pick out, I don't see what the justification is for
It would
picking
be
out.
the same kind of justification, because those guys, the percentage of experiments that they're deceived about is smaller, okay? But they're still not, they're not people who are investigating the world in the way you take yourself.
In that scenario, all of these people would be assuming that they were in the truly cognitively stable environments, and they would all be wrong. So
Yeah.
the chances that you're a person who is right under that description is very, 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 very small.
The second doesn't follow from the first. But
I think it does, but we
we
should.
can talk about it. Good.
So, with granting external inflation, it seems like the inflationists can say something a little bit more, which they can say that you're going to have these post-Big Bang regions, some of them will have different values of initial entropy, some of them will have low entropy states as initial conditions, and those are the ones which will look like the past hypothesis is true. We ourselves have a lot of evidence that the past hypothesis is true. Therefore, there's observational selection. We're only going to find ourselves in those inflationary bubbles in which that happened to start at a low entropy state, even, as long as the measure is not completely zero.
We don't have any evidence at all of the past hypothesis. That's why it's a past hypothesis, not a past observation.
Well, we have evidence that there was a consistent history of the world.
Yeah, no, that doesn't seem right, Sean. The kind of evidence we have isn't like the evidence that there's a chair here. It's like the evidence we have from laws. It makes good predictions. You plug it in, it works well. It rewards your using it in the way laws do. That's the kind of evidence we have.
If I was a Boltzmann brain, I wouldn't expect to see the CMB density fluctuations to conform to the lambda CDM model.
But the converse does not follow. Because you've seen the CMB conform to lambda
Right.
CDM does not mean you're not a Boltzmann.
Okay.
That's why we don't have evidence for the past hypothesis. We need it to make sense. So there is, I mean, on the table, I should be more fair. There is the possibility that indeed the universe is full of Boltzmann brains and all sorts of craziness. And we can escape the cognitive instability just by holding our breath and stamping our feet and saying we're one of the good guys. That is a possibility. The other possibility is that this is not the right cosmology of the world. In the right cosmology, there aren't that many Boltzmann brains. I like that possibility much better, therefore I'm going to try to make it true. I may or may not succeed. Yes?
Okay, so I have a very simple question.
Okay.
You say your argument for inflation is that it makes predictions which are reasonable. Now I'm asking, how can you say that inflation makes in our local patch predictions without having solved the multiverse problem, which says, because without having a measure, the only prediction inflation makes is that we have a multiverse.
No, that's exactly right. That's what I'm saying.
Okay.
I'm saying, so I haven't finished the dialogue yet because there have been questions. But if you remember where the dialogue was, there was, oh, I can explain the fine-tuning of the early universe. All you need is a little patch of false vacuum. No, that doesn't work because you need to fine-tune more to get that patch of false vacuum. Wait, that's okay, because as long as it starts once, you get an infinite number of good things. Then the skeptic comes along and says, yes, and you get an infinite number of bad things. And the sensible way of counting the bad things outnumber the good things, so you actually don't explain anything at all. And that is essentially the state of the art right now. We're at a condition where if inflation works, it doesn't work for the reasons that we originally thought it worked. That doesn't say it doesn't work, but we need to be a little bit more sophisticated. We need to solve this measure problem.
Sean,
Yeah.
this is really quick. It's not about the Boltzmann brain stuff. I think this is what Allison was confused about a minute ago, and maybe the answer is, I don't know what. The step from what I take it was the second step from the dialectic to the third was confusing. That is, the second step says, yeah, but what you need to get inflation started is even rarer than what you needed to get the ordinary Big Bang started. Right. And the next step in the dialectic was, yeah, but once you do get it started, everything is great. What's the structure of reading the third thing as a response to the second? It's still.
The third thing says, what I should have meant by generic initial conditions, or easy to get initial conditions. What someone like Andre Linde would have told you back in 1984 was the most natural thing to have in the early universe is wildly fluctuating chaotic stuff with Planck scale changes from place to place.
Okay.
And there'll be one little spot which is dominated by the false vacuum, and that grows.
Okay.
These days, very few of us believe that a generic initial condition is wildly fluctuating Planck scale stuff, but instead you can say, well, I should be talking about the wave function of the universe. There's a quantum probability for certain degrees of freedom to be in certain configurations. And as long as there is some non-zero probability somewhere for there to be a little patch of space ready to inflate, I get an infinite number of observers.
So this is all going to depend, it sounds like, on one way or another of solving the quantum mechanical measurement problem. That is, of making these fluctuations into actual events rather than mere expectation values.
I think that's fair.
You're going to be nowhere if you just start with an eigenstate of the Hamiltonian and it just stays that way. Okay. So somewhere getting this started is going to depend on having some kind of an attitude or other toward how you solve the quantum mechanical measurement.
I'm very happy to say yes.
Right.
I'm not speaking for the community in saying that, but I would be very happy to say yes.
Right.
I think that many things depend on solving quantum mechanical measurement problem.
Good. What one might not have. Good. Okay. But good. Among them this. Right.
Among them this. Yes, that's right.
But can I just a follow-up? But I don't think that you would be ready because doesn't you need a prepared initial state even if you solve the measure problem?
No, if you suppose you solve the measurement problem, I'll say GRW. I mean, in any way of solving it, every GRW. But suppose you solve it with GRW, okay? Then you have a vacuum. It's a fact about these vacua that they just, notwithstanding being eigenstates in the Hamiltonian, they don't stay that way. They actually fluctuate. There's actually time dependence.
But what I'm asking is, how do you know which kind of eigenstates your vacuum has?
I take it I don't know what you mean by which kind of eigenstates the vacuum has. The vacuum is a state, or some set of states.
Yes, but for example, the cosmological constant problem says that we expect a different vacuum than we have. Okay.
You're probably just talking over my head. But I'm not
Maybe
sure.
I don't. So I just thought I'm not sure if we understand what the wave function of the universe is, that we can get rid of the initial conditions problem. If we can define the wave function without putting something into the theory which is not within the theory. So if we
You need to tell me more about this,
Okay,
but let's
yes,
let
sorry.
Sean talk. Sorry, Sean.
Sorry.
And I said it would be short.
That's my fault, sorry.
I didn't believe you.
I didn't intend you.
Very, very quick clarification. You want a theory that says the measure on Boltzmann brains a priori should be small, rather than saying anthropic selection allows us to expect to predict that we're not a Boltzmann brain. The first is
doesn't.
stronger.
Yeah, no, anthropic selection is completely useless.
I agree.
It's not nearly good enough. I mean, anthropic selection totally allows us to be Boltzmann brains, or Boltzmann rooms, or Boltzmann solar systems. Here we are. It doesn't say anything about what's outside. This is the best argument that the anthropic principle does not solve all of your problems. That you need something more specific, and therefore you should be skeptical about in the anthropic principle solving any of your problems.
You need reason to believe in a multiverse to begin with to use anthropic reasoning at all.
Sure.
So it begs the question if we're dealing with index conditions for internal places starting in the first place.
Sure, that's fine. All right. Okay, so where were we? We're at the stage in our dialogue where the skeptics of inflation have had the last word, and the advocates are given the homework problem of coming up with a measure that makes sense and solves the problems and is true. There's been advances in the first two steps. So what people try to do is they invent different measures, and they try to show that they're not completely incompatible with observations. And there are claims that that has been done. There are no claims, or there is the case that those kinds of measures are actually what is predicted by the theory are much harder to establish. So I think that the philosophy is, first let's find some way of regularizing these infinities, which is not obviously wrong, and then we'll hope that a miracle will occur, and we will realize that that is actually what the theory is predicting. I don't want to be unfair. I think that, yeah, there's probably another right person to be giving this talk, because I'm very skeptical that we had anything good yet, but others disagree.
Sean, when you say measure predicted by the theory, you mean sort of made natural in the way that volume measure is made natural by the, okay. That's
Something
very
like
far
that.
from being predicted, as you yourself has emphasized. There are plenty of other measures that are compatible with the equations of motion. It's just that there's one
Some measures
that
are better
plays
than others.
nicely with them
Yes, that's right.
in a way that's hard to make the argument why that means
Exactly
it's
right.
a measure.
That's
Okay.
Yeah, so just to be clear, the earlier cases where you're discussing measure, you have phase space, and you have Hamiltonian, so that allows you to introduce a very different kind of measure over the phase space of the theory. I've always been a little unclear what it would mean to have the theory determining a measure on this, because this is just a measure over this big universe.
Yeah, that's right.
It would be something to do with the dynamics with the generation of the, so if you had a dynamical theory governing how these bubbles are generated, then that would give you like a measure? Is that the picture?
You need to work. No, you need to work harder. I think you need a little bit more brain work in at least two different ways. One is, what do you mean by a measure over different appearances of indistinguishable macroscopic data? And number two is, how do you regularize the infinities? And neither one of those is implied by the Liouville measure itself, I don't think. I think you need a little bit more of fancy footwork, which we don't have. I'm not, I'm trying to be honest about this. This is what we need. Is what I'm saying would make sense of this thing. So let me, good. Even though I'm a little skeptical that any of the measures currently on the market work, it's useful nevertheless to have in mind what people are talking about. So there's two kinds of measures. One is global, and guess what the other one is? Global. Good. The global measure is what we did here. You take the limit of some volume of space-time as, I guess both measures are like that. That's not a good way of characterizing it. The global measure looks at all space-time. That's why it's called global. So that's what we were doing here. We were slicing, we were including all of the de Sitter space background, all the little bubbles inside it. We were regularizing it in a certain way. The most naive regularization fails miserably, and therefore the game you play is to replace t by log of t, or something like that. You play games where you change the rate at which the volume is counted as you go to the future. So you replace what is called, this is the proper time measure, you can get the scale factor measure, you can get other games you can play there. But there's a whole other thing to do, which is the local measure, which is actually inspired, I think, by, back here when we were talking about, I mean, this is going to eventually be important, horizons and horizon complementarity. Remember, the moral of horizon complementarity was you shouldn't simultaneously talk about what's happening on two different sides of a horizon. Here, up here, there's many, many, many horizon volumes on any one of these space-like slices, and we've been talking about them very bluntly. So the local measures say, stick to a causal patch. There's different versions of local measures, but again, morally, this is what is happening. So rather than taking some space-like initial condition and following up the whole space-like slice to the future, take an observer on that space-like slice, follow their world line to the future, and rather than asking what happens at a typical location in space-time, ask what happens along a typical trajectory, what happens along a typical world line. So this trajectory gamma comes along with a volume of space-time that is the interior of the past and future light cones along that trajectory. So if you start down here and you go up, you build up bigger and bigger diamonds, causal diamonds as they're called. And as time goes along, you can calculate the number of events in that causal diamond, or just calculate the number of events within some region, some thick world tube around that, or something like that. Yes?
What do you mean by typical trajectory?
Well,
so you like pick an
that's-
arbitrary trajectory and then the measure will give you a sense of what's typical around that.
that's right.
So it wouldn't give you a notion of typical trajectory.
So that's right. So when you say typical trajectory, that is code for a process by which you say you do it for a trajectory, then you do it for lots of other trajectories, and you hope you get the same answer. If you don't get the same answer, then you say you failed, and your measure is no good. Or, you know, the implicit hope of everyone who is trying to rely on inflation to explain the cognitive stability of our environment is that the quantum state itself doesn't matter that much. That you don't need a separate theory of initial conditions. All you need are the dynamics of inflation. And following that, and that may or may not be true, that's the hope, right? That's the aspiration. So following along that philosophy, what people try to do is to develop measures that are not sensitive to where this trajectory was, or which bubble it hit first, or where it was pointed, or anything like that. Again, that may not be the right thing to do, but if that works, then you can claim robustness. And this philosophy is compatible with the moral of horizon complementarity. You're only talking about what happens inside some observable region. And you say that all this stuff that you thought was an infinite number of bad observers, that's all sort of encoded on this apparent horizon in some complicated way that I don't need to worry about. That would be the proposal. I'm not going to pass judgment on any of these measures. I'm just saying this is the state of the art. I think that I have told you what this is. This is a contemporary argument that people are having about this stuff. Yes?
There's another argument in favor of some of the measures, which is that, like, for example, Busso has shown that some global and some local measures seem to give the same answer.
Sure.
So they're mathematically dual, and that's a clue that maybe you're on the right track. What do you think about that?
I don't think that's a very good clue.
Because they both could be wrong in exactly the same way?
There are many ways to be wrong in exactly the same way. Yeah, I'm a big believer in the number of ways being wrong to be very large.
But it could have failed. I mean, you could certainly be wrong if you had two that gave different answers.
Look, I really think that getting the right answer is way insufficient for saying that you have the right measure. I would like to derive the measure.
Sure.
And I don't think that anyone has done that.
And this is the first stage for guessing, and then later you have some better theory that tells you, oh, okay, I should have predicted this measure in advance from this theory.
But isn't it so, I mean, I'm a bit skeptical about this equivalence because you need, if you take all these measures, then for some measures you need special initial conditions for the measures so that they are equivalent before measure. There are some papers on it. So they are not independent, but what you assume about measures, they give you equivalent, but if you assume different things about the measures, there are papers 2 or 3 with I think Matt Johnson, who was here last week, is co-author with John the credences of one of the papers. They show it that measures are only equivalent if you, with time cutoff, and so it's all these things, if you assume something about them. So they are then basically not independent of their own initial conditions if you want equivalence.
You're saying you can tweak a global measure to be equivalent to a local measure only with some additional
Yes,
settings?
yes.
So you're perhaps hiding the equivalence, it's not natural.
Well, I would say that if you assume, what's the reason that to assume that conditions which make those measures equivalent and not to assume different conditions which make those measures not equivalent or inequivalent? That's my question. If you can explain why those are the best conditions and why we are not allowed to assume other conditions, then okay, that's fine. But unless you can, if you cannot explain that we are free to assume something else and the measures are not equivalent, so they are only equivalent under certain conditions, and I think it's
Certainly, you take the global-local duality more seriously if you didn't have to add extra something to either of them.
So my personal point of view is that none of the measures we have right now are especially compelling, but that is not to say that we won't get one. You can have your own point of view. It's definitely not a settled subject by any stretch of the imagination. Let me have 2 more cool things to say in the next 20 minutes. So I can include 1 cool thing in a 10-minute each, then we're good. Cool thing number 1. Well, oh no, I had a 3rd cool thing. Wait a minute. That makes it harder. Okay. Yes, I have 3 cool things to say. I'm going to talk fast. The first is, like we were just saying, this story, despite the fact that it seems to follow relatively painlessly from simple laws of physics. I mean, the consequences are painful, but the picture just falls out of the equations. It does nevertheless involve a lot of physics that we don't know, a lot of places in the universe we don't know, a lot of things we don't have empirical access to. So what about the real world? Remember, the real world has vacuum energy, or at least it has something that is causing the universe to accelerate. What if it is just a vacuum energy, right? I'm not even sure if I can draw a picture of this, but let me just say it in words. The real world is described by Cosmology's favorite model, which is lambda CDM. Cosmological constant, cold dark matter, baryons expanding. As Fred has told us, what's going to happen in the future, the black holes will evaporate, stars will die out. If you wait long enough, you will be in an increasingly accurate approximation of de Sitter space, empty de Sitter space. De Sitter space, we said, has a temperature. The temperature of de Sitter space in our real world is something like 10 to the minus 33 electron volts, which is something like 10 to the minus 30 Kelvin, which is much, much colder than the current universe, but still not 0. This means there is a chance that you will fluctuate into a Boltzmann brain, or a Boltzmann room, or a Boltzmann solar system. This is a temperature that lasts in de Sitter space, and it lasts forever if you're just in de Sitter space. De Sitter space goes forever. There's no future boundary to it. So there's a probability that you fluctuate into a Boltzmann brain or whatever, probability per unit space-time volume. And the volume of space-time is infinite. So even without inflation, eternal inflation, landscape, or anything like that, real cosmologists' favorite real theory of the real world predicts, unless you can fool with your measure, predicts with overwhelming probability we are Boltzmann brains. That's the actual prediction of our favorite theory of the real world. So maybe you can escape by saying, well, I just put myself after the Big Bang. Yes, there will be an infinite number of versions of me in the future, and they will all be terribly wrong, and it's a tragedy. I'm the happy one who lived after the Big Bang. But I personally don't believe that's fair, and therefore I believe that lambda CDM has a Boltzmann brain problem. Now, you can try to escape it. You can say, well, maybe there will be a phase transition in our future. Maybe de Sitter space is not eternal. Maybe there's some scalar field that can undergo quantum nucleation to a lower energy density vacuum that will save us from the Boltzmann brains. And it turns out that there is a scalar field that might very well do that. It's called the Higgs boson. So the Higgs, which we discovered last year at this time, almost exactly 1 year ago, is a complicated story. It's an SU2 complex doublet. It breaks electroweak symmetry. Forget about all that. It's a scalar field with a potential, V of H, as a function of H, that looks like this. So V of H looks like minus 1/2 mu squared H squared plus lambda H to the 4th. So there's, again, a minimum here not at 0. There's a small vacuum energy, and it breaks the electroweak symmetry, and we know that it exists because we found it at the LHC last year. However, this potential, and you say, well, this potential is not that potential, because this just has a minimum, this one has 2 minimum. That's important to this story. But this is the classical potential. There are quantum corrections to this potential. So when you write mu and lambda, this lambda in particular, which is what gives you the positive energies at large h, this lambda is something that actually depends on the energy scale at which you measure it. That's the renormalization group. When you measure parameters in quantum field theories, they're energy dependent. So I don't know why they did this, but aspiring young particle physicists calculated lambda as a function of energy. So lambda effective, if you like, as a function of the energy at which you measure it. And it's a small positive number, but it decreases as the energy goes up. And in fact, now that we've measured the mass of the Higgs boson, we know lots of other things about the standard model. If you just assume the minimal content of the real world, top quark, Higgs boson, etc., it goes like this. It goes negative at large values. And what that means is that this Higgs potential does this at large values. And then you have an interesting question in front of you. Does it go like this? I should do this as dashed lines. Does it go like this? Or does it go like that? And the answer is that within the current experimental error, all of these are open possibilities. These are allowed by the data. So it is possible, in fact, the favorite thing is like down here. The middle of the known values are ones for which the Higgs is unstable to bubble nucleation. So our vacuum is not eternal in the real world, even without the string theory landscape and all that other nonsense. It seems to be that unless you put extra physics at high scales, we live in an unstable vacuum. So then, you play this game. You say, all right, we're going to live in the center space, but there's going to be bubbles, and they're going to nucleate, and what's going to happen? And the answer is, it depends on the lifetime, obviously. So you need to actually look at that potential, and actually need to calculate that factor, the Euclidean action. Fred, I don't know if anyone else did, but Fred briefly mentioned that when you tunnel like this, the rate goes like e to the action that you calculate. And that action is going to depend very sensitively on details of the potential that we know what they are if there's no new physics. If there's new physics, they change. But you can estimate what that action is and what the tunneling rate is. So if you look at the bubble nucleation time it takes for us to run into a bubble, on average. If the bubbles nucleate very quickly, then there's no Boltzmann brane problems. They just percolate, right? So if the time is very short. So down here, what time is that? That is an astrophysically fast time. It's about, Don Page calculated to be about 20 billion years. It's roughly the Hubble time now, but let's be cute and just call it 20 billion years. So below here, you percolate. There's no problems, no Boltzmann branes. You don't have time enough to make any Boltzmann branes. You escape our current vacuum. That's the good news. The bad news is that we could die any minute. That none of Fred's talk is right. You don't even have time for stars to, do all their red giant blue dwarf stuff. The universe is going to completely be in a different phase in some quick period of time. There's an upper limit, which is the time for which the rate of forming Boltzmann branes is just naively greater than the rate of forming bubbles. So here, but that's an incredibly long bubble nucleation time. E to the 10 to the 50 is an estimate. If you ask me what the units are, it doesn't matter, because e to the 10 to the 50 Planck times is equal to e to the 10 to the 50 gigayears, to this approximation. So if the bubble nucleation time is that long, then there's no hope. Then you're going to get too many Boltzmann brains in nucleus. In this intermediate regime, you need to get a measure on, I can't spell anymore, dependent. Depends on who wins versus the Boltzmann brains versus the bubbles. The best current estimate is that we're here. We're in between. So all I'm trying to say is that the cosmological measure problem is very plausibly a real-world problem. There are all sorts of cheap ways out, like saying that the vacuum energy is not constant, we will roll down in the future, some quintessence-like thing. But this idea that we need to understand how to do these calculations is not necessarily just philosophy. It's not necessarily just completely abstract cosmology. It is actually forced on us by very simple theories of the real world. All right, that was one cool thing I had to tell you. Cool thing number 2. Any questions about that? Yes.
Can I ask a question? So, if you have this most probable potential for the Higgs, where there is a true vacuum or a truer vacuum on the right, and we have bubbles appearing fast enough that we move into it, would we expect that in the distant future of that universe there would be Boltzmann brains, and is that a worry?
So if your future vacuum has a negative cosmological constant, then in the interior of the bubble you hit a big crunch, inevitably. You don't actually, you might expect that you settle down to some anti-de Sitter vacuum, but remember, anti-de Sitter focuses energy, so you hit a future singularity inevitably. And then the question is, do you continue through that singularity by resolving it somehow, or do you just, does space-time end? I, as you know, am on the, you need to continue through somehow. Other people act as if space-time ends, but it's an open issue, not true. Yeah?
If you believe that space-time ends in a terminal vacuum where you have negative lambda, is that a way to give you a cosmological arrow of time?
No, because the same would be true in the past. In fact, that is exactly what I'm talking about right now. The second cool thing I want to say of the 3, relating the landscape to the arrow of time. So, and this is a very good, interesting, cool, but I think fundamentally flawed paper by Raphael Russo, where he tries to, I argued before that the Anthropic principle is not nearly enough to save you from Boltzmann brains. But Raphael tried to combine the Anthropic principle with this series of vacua and string theory landscape to solve the arrow of time. So what he says is, imagine that there's a potential that's a little bit more complicated than that, but there's some scalar field which schematically has potential that looks like this. So this is very precisely drawn. So this is vacuum A, B, C, D. In D, lambda equals 0. C is where we are today. A is a vacuum with a lower vacuum energy than ours today, except that to get from A to C, you need to go through B. And the twist is that he says, maybe the local laws of physics are such that intelligent observers can only exist within vacuum C. So that even though the entropy of vacuum A is higher, because the cosmological constant is lower, there is no one there to witness that. And then he says, well, vacuum D is just Minkowski space, there's no fluctuations, there's no brains or anything, it's just empty space. So even though the entropy is infinite there are no observers there either. Maybe the laws of physics don't allow you to have observers. So he says a natural place to begin is the highest, is the state with the highest entropy that is not infinity, which is A. And from A, if you wait long enough, you will fluctuate upward to B. And then in B, you inflate, because it's a high energy density vacuum. And eventually you reheat, you fall back into C, and that's where we live, and then eventually C dies off into D, and then the universe just quiets down and stays there forever. And he says the point here is that we live in C, but to get to C, we had to come from B, and that's why inflation, and therefore we're ordinary observers. We live in some post-Big Bang, cognitively stable environment. So, probably, since you've been here for 2 weeks now, you know what the problem with this is, which is that I should also be able to ask where this came from. If I'm claiming to solve the arrow of time problem, I can't assume a quote-unquote initial condition, right? I need to assume the condition of the world and then evolve it forward or backward in time. I'm claiming to solve it dynamically. So where did A come from? If I trace the past of A, I'm going to get, according to the time reversible laws of physics, the same trajectory, just backward in time. I didn't quite balance it out here. You know what's going to happen. So what this is saying is that from the space-time picture point of view, if I draw the typical eternal inflation space-time diagram, conformal diagram, it looks like here we are in A, well, do I want to draw this? No, I don't want to draw this yet. It's too complicated. Let me just say it in words. So the argument is A is higher entropy than B or C. D is Minkowski space. There's no reason to fluctuate into anything at all. So the highest entropy place we could start is A, and then we go to B and C and D. The problem with that is we should have come from B and C and D, and you just said D is Minkowski space, so there's no reason for it to fluctuate at all. But look, you're saying that it did fluctuate from D, or at least evolve from a Minkowski vacuum into C. And that requires that you're not actually in the vacuum of Minkowski space, right? So in de Sitter space, you can be in the vacuum and there are fluctuations. In Minkowski space, the temperature is 0. There's no thermal or quantum fluctuations, but you can literally have Minkowski space with stuff in it, and that stuff can evolve in such a way that it pushes you over into C. So the flaw in my mind in this kind of argument is that it is assuming that you can evolve from C to D, but you cannot evolve from D to C. And I think that that is putting in an arrow of time pretty explicitly by hand. But once you say that's cheating, and therefore if I can go into D, I can come out of it, then you realize that there's no role at all played by A and B. If this can happen, then so can D, goes to C, goes back to D. And if that can happen, then there's no reason for inflation, there's no reason for the Big Bang, anything like that. So I do not think that, as we currently understand it, merely evoking the Anthropic principle plus the string theory landscape helps explain the arrow of time. Yes?
Can you say I didn't quite get the very first step where you said when we take the state and then A revolves the loss backwards, we get the very same sequence?
Yeah, you just said it very well. Excellent.
But it doesn't seem, if I have
Why
like
should it be
stars on the
different?
floor and I walk them forwards and I walk them backwards, they get very different. Like
This-
what's the vibrate state? Why should this?
This is a vacuum state. This is time reversal invariance state. There's no directionality built into it at all. You're sitting there in a vacuum. There's no reason why future evolution should be different from that state.
Okay, that's good.
Unless you put some arrow time in my hand. Yeah, but otherwise not.
So C is the region where there's a post-Big Bang universe and we have ordinary time evolution in the way we...
Well, B is the reason why. C is where we can live. Yeah, C is where we are now.
In a lot of these discussions, it seems like there's sort of a presupposition of a semi-classical space-time in which the field lives, where it could decay or it could not. So it seems like there's an arrow of time that's put in already, and you're thinking about what's the probability that one vacuum will transition to another.
Where's the arrow time put in? Sorry.
Well, I'm not sure that it necessarily goes in either direction. I'm just asking more about the assumption that there's some background space-time in which the field is living in, and it could decay.
Yeah, it could decay and it could have undecayed to get there. Those are both equally likely. So I don't think I'm putting in an arrow time anymore.
Okay.
But so I don't want to, I'm saying that I don't think that this is right. I think that it's flawed by itself. But, I mean, it's clearly interesting. There's something going on here. If there were some reason why cosmological trajectories of this form, or even of the form D, C, B, and then back to C, and back to D without involving A at all. If there was some reason why trajectories like this dominated over trajectories like this, I think you would win. I think that would be good. You would explain something. I see no reason why they should dominate. They are harder to have happen. There are fewer of them in some ordinary counting. But that is what you would want to have happen. It could be that the quantum state of the universe is peaked on trajectories like this or this, rather than like that. It could be that the truth is not independent of the quantum state, but that there is some classification, the Hartle-Hawking wave function or whatever, that says that things like this are what dominate. Yeah.
So a question about the broad strategy. So in order for eternal inflation to be a satisfactory solution for the purported problem that the initial state of our universe on some natural measure that's suggested by dynamics is incredibly unlikely, it had better not be the case that there's a measure which is suggested naturally by dynamics of the total physical theory, according to which the potentials which actually produce eternal inflation are incredibly unlikely. Do we have any reason to believe that's not the case? So my worry is, like, isn't this just pushing the problem further and further back?
You're talking about the measure on the space of potentials?
Yes.
Yeah, I have no idea what that is.
Yeah, but what reason do we have for thinking that the total physical theory, whatever that is, has a natural measure on it, and on that natural measure, the space of potentials which produce eternal inflation are going to be very unlikely?
Yeah, well, two things. Number one, I do think it's a separate problem. I think that even if we assume that there is some individual potential, we just don't know what it is, we still have this problem about which solution dominates. On the other hand, there's the hope that string theory gives you the right potential, and that's it. Right? There is some theory of everything, and there's not a measure on it, there's just a theory. And asking whether that theory is natural is different than asking whether or not the history of the universe is natural.
Sean, isn't this potential in the full-fledged fundamental string theory, this potential is going to be part of an effective theory, no?
Sure.
And so it's going to be a function of what the state in the full fundamental theory is. So a measure over that set of states is going to imply a measure over these potentials.
So yeah, that's right. So but what I really meant, you're supposed to be able to translate in your head. What I meant was that there is a Hamiltonian of the universe, and it just is what it is. And people have asked, you can describe a Hamiltonian by listing every energy eigenvalue, right? Or the spectrum of energy eigenvalues. So Andy Albrecht wrote a paper where he said, could the Hamiltonian of the universe just be a random Hamiltonian? There's the semicircle law. If you have a random Hamiltonian in a finite dimensional Hilbert space, you can actually plot the spectrum of eigenvalues. And he says, is there any chance that looks like the real world? That's an interesting question to ask. He says the answer is yes. I don't believe the answer is yes.
I don't understand how that translation helps. Maybe I'm misunderstanding you, but what you seem to be nodding your head to was, what you're calling the Hamiltonian of the universe, which includes this potential, isn't really the super capital H.
No, but that's what I meant. So when I said that it is the Hamiltonian of the universe really is the super capital H once and for all done. This is all some effective description of that in some background.
Good. So it looks like that, it looks like talking about a measure over this potential really is equivalent to talking about a measure over fundamental quantum states. It's not a different thing. Because different fundamental quantum states are going to give rise to different effective Hamiltonians.
I think that is part of it, but not sufficient.
What's part of what?
No, so if you want to know a measure over the space of effective potentials, the measure over the space of quantum states is necessary to know, but obviously not sufficient.
No, okay, but it's going to be parasitic on such a measure. Good. Okay, good. I think that's what he was asking.
Good. So this is the state of the art with respect to the landscape and eternal inflation. I don't have anything to add to it. It's interesting to think about. I don't think it's anywhere near done. I'm officially out of time. The other thing I could possibly tell you about, if you give me 8 more minutes, is a toy model of phase space and how it relates to global versus local measurements. So if you want me, let me see, I'm supposed to make it easy for you to not raise your hand. So if you want me to keep talking for 8 more minutes, raise your hand. That's close enough. All right. You're just polite. Okay. So this is all very highbrow and interesting and ambitious and hard, and I don't think they were anywhere near the final answer in this stuff. I don't think it's hopeless. I think that progress is being made. I don't think the progress is going to be finished anytime soon. So what I like to do as a simple-minded physicist is think about the simplest toy models, the spherical cows, in which things like this can arise. And the basic difference, so one thing we can do is forget about quantum mechanics and Hamiltonians and just think about classical phase space. We can think about two-dimensional classical phase space. So there's one coordinate and one momentum. You should be able to do this. In fact, we can think about the simple harmonic oscillator. There's a potential V of Q, if Q is the coordinate, 1/2 omega squared Q squared. And if the universe were like that, then I think we would not be able to explain anything about the arrow time, etc. Because of the recurrence theorem. In this phase space, we go Q, P, the orbits all close. So anything that can happen happens an infinite number of times over and over again. Low entropy things are going to be much more rare than high entropy things. You should expect, in the quantum mechanical version of living in a classical phase space with bound orbits, is to live in a Hilbert space with a finite dimension. With a finite dimensional Hilbert space, there's a quantum recurrence theorem, and whatever state you're in, you come back to that state arbitrarily close an infinite number of times. So I claim that if you live in a quantum mechanical theory with a finite dimensional Hilbert space, it would be absolutely impossible to solve the arrow time problem, if quantum mechanics is correct. What you can do is go from bound orbits to unbound orbits. So you look at the upside down simple harmonic oscillator, which is minus 1/2 omega squared. And then your orbits are no longer bound, but they do have some structure. So if you plot Q versus P, then you draw diagonal lines at Q equals plus or minus P, and there's a simple thing that all the orbits do. They either go like this, or like this, or the other way. They go down towards this way. So what does this mean? This means that if you have a positive momentum when Q is 0, that means you're up here, and you're moving to the right, and you'll go up here. And likewise, you can fill in all the other options. So this is a solvable problem, and the question is, what questions are we allowed to ask about what is likely in this kind of scenario? Phase space is infinitely big in this scenario. There's no normalizable measure that is given to you by the theory. The measure, the Liouville measure, is dp dq. It's just flat. The volume is infinite. It's no how. You ask, what does a typical point in phase space look like? That's like picking a number between minus infinity and infinity. It's not a well-defined problem. So you might say that, so the point is that if the orbits are bound, you're a Boltzmann ring. You should be a small low entropy fluctuation. If the orbits are unbound, you have a chance of not being a Boltzmann ring, but on the other hand, you say you have a measure problem and you can't explain anything. So the global, this would be the global measure. Just put a measure on all phase space like that. But notice that if I have some arbitrary blob in phase space, Liouville's theorem says that its volume stays the same, but its shape takes a very particular form. It gets stretched asymptotically close to that line, P equals Q. So can you make any money out of that? Can you say that even though the phase space volume is conserved, there is something that typically happens along a trajectory? So the global measure says what happens in phase space at a point. The local measure says what happens along a typical trajectory. And the nice thing is that in this toy model, all the trajectories are equal. They all do the same thing. So if I ask you to pick a random trajectory, you can't. There's an infinite number of them. But it doesn't matter that you can't because they all do exactly the same thing. They all do that. And therefore, let's ask what is the fraction of, let me ask it this way. If I pick a random point, should it be true, let me write this down, that the absolute value of the absolute value of Q minus the absolute value of P is less than epsilon? What this is saying is the absolute value of P close to the absolute value of Q? Now, so that's saying that there's some thickness here near these diagonals. What is the chance that I live within that colored-in band? And there's two possible, sensible, immediate answers. One is it's very small, because as I draw bigger and bigger volumes here, the area of the shaded region grows linearly, and the area of the unshaded region grows like the area, right? Therefore, my global measure has failed me. The chances of being there are very small. The better answer is to say that's an unanswerable question. I could pick some weird way of drawing my shapes as they grew so that almost everything was inside the shaded area. So the global measures are just ambiguous. The local measure says pick a trajectory. I didn't draw my trajectory very well here. But I follow a trajectory, and the measure on the trajectory is just dt, the time coordinate along the trajectory. What I notice here on every trajectory, if I first pick the trajectory and ask what a typical point looks like, there's a finite length for which this is not true. And there's an infinite length for which this is true. So I would claim that in the local measure, instead of asking what does a typical point in phase space look like, what does a typical point on a typical trajectory look like, there is a sensible, unique answer, which is that on a typical point, on a typical trajectory, the absolute value of P equals the absolute value of Q. Can I justify why I should pick that procedure for doing it rather than some other procedure? No. But I think this is suggestive. The idea is that if we did want to solve this cosmological measure problem and explain the arrow of time, there's the hint that by asking the question correctly, we can get a robust answer even in an infinitely big space. I think the space of states needs to be infinitely big. So therefore, I think that we need to have some way of calculating what is likely and what is unlikely. This toy model suggests that maybe there is. All we need now is to make a cosmology that looks like the toy model, and we'll declare victory. So maybe next year we'll come back and we'll have that done. And with that, I'm done. Thanks. Yes.
So, by way of pulling back to a very long view here, we start out with this Boltzmann problem. Take as given whatever you like, whatever you think is directly available to you about the present macro state of the world. This room, the solar system, the whole universe now, whatever. Okay. Boltzmann has this argument that towards the future, its entropy is going to go up. That's the good news. Bad news is that the minute you remember that the fundamental equations of motion are time reversal symmetric, it implies the same thing about the past. Good. And we have this standard stratagem for getting out of this, which is positing some past state. And then you kind of look at this and you say, that's fine as far as it goes, but I'd like a way to get the past state out of the dynamics rather than positing it. Good. Here's what's puzzling about the whole strategy. The dynamics you're considering remain time reversal symmetric. Presumably, the crude outlines of the Boltzmann argument about entropy increase toward the future are still in place. Okay. You specifically want a strategy that doesn't involve positing some state at some other time. What goes wrong with the Boltzmann argument?
What goes wrong is that well, what hopefully goes wrong with it would be that there's an order of limits question. There's an order of asking questions question. Take up a particle rolling here in this potential. If I just tell you what is its q, what is its coordinate,
Right.
and I don't tell you what p is,
Right.
you have no reason to prefer positive p to negative p. The phase space is equal, right?
Okay.
I mean, I'm drawing a line, there's at a given value of q, there seems to be a reflection symmetry between positive q and positive p and negative p. There's no reason to prefer p to be positive or negative. So if I asked you, what do you expect p to be? You would say, on the basis of my local measure on phase space, I have no preference for positive or negative. But there's a different question you can ask. You can ask, this was supposed to be the point, I know I was rushing, but this is supposed to be the point of this example. The other question you can ask is, pick a typical trajectory. And then ask, along that trajectory, what do you expect to get asymptotically as q becomes very large? And I think the answer is that q equals p, plus or minus. So that's a different answer. Whether or not it's an interesting answer, it's a different answer than you got by first picking the point. By first picking the trajectory and then looking at typical points on the trajectory, you get a different answer than just by looking at what is allowed in phase space around the local
Hang on
point.
a second. Hang on a second. I still don't get it. At the end of the day, we're going to have some rudiment of the Boltzmann argument, which is the only reason we believe in the second law of thermodynamics going forward. So whatever the measure is,
Right.
it's going to preserve the Boltzmann argument.
Well,
Otherwise,
to
we're
exactly
not in a
the same
position to
extent.
have- Then here's the worry, okay?
would you say the Boltzmann argument is preserved when you posit the past hypothesis?
What? Sure.
Okay, then yes,
Okay.
for the future.
What? Well, but so now I don't understand. Where does the time asymmetry get introduced?
The time asymmetry gets introduced because you say that in all the ways that this local data could be realized, when they are realized, in almost every time they are realized, they're in the middle of a strong entropy gradient. They're not the minimum. It's
No,
a
but
different
that's what-
measure.
No, but this is, but you say in all the times along a typical trajectory without positing an initial condition. I mean, so I'm still missing something. Look, we have the Boltzmann argument, which maybe you think about modifying this argument. I'm not sure. The standard Boltzmann argument is, I give you some macro state. Okay, I give you some macro information. Okay, I have some measure over the micro states compatible with this macro state. Presumably, the measure itself doesn't introduce a time asymmetry, or is
That
that
measure
not-
doesn't. I'm
Okay.
saying that cosmology gives you a different measure.
And how is it going to do that?
Because cosmology says that rather than looking at all of the microstates compatible with your macro state,
Right.
you look at the actual appearances of that macro state in the cosmological trajectory.
But if you talk about a cosmological trajectory, you're effectively introducing, say, something like an initial state. The question is, in what sense are you not here introducing a past hypothesis? In the sense of, say, positing the initial vacuum out of which things nucleate, or something like that.
In the sense that in this potential, every trajectory has some turning point, has some special value. But every trajectory has a turning point. The existence of a turning point is not a special posit. You can't help but have a turning point somewhere. So I'm not making,
I still don't.
the goal would be that nowhere in choosing or deriving your cosmological trajectory, do you ever assume that the entropy is low compared to any other particular number.
No, not compared to any other particular number. We can continue this after if it just keeps going back and forth. But the standard argument that gets you into the worry has a very simple logical structure. One, there's some measure over the microstate compatible with the macrostate. Two, the Boltzmann, something like the H-theorem argument, starting from this measure, works toward the future. Three, the time reversal symmetry of the equations of motion. You take those three together, you've got the conclusion that wherever you are, you're overwhelmingly likely at an entropy minimum. We want to avoid this conclusion.
That's right.
You must be negating one of these elements. You must be disagreeing. Which
The
one
measure.
is what? You mean the claim that the measure is time reversal symmetric?
Yes.
So
Because what you're doing is replacing the time reversal symmetry of the measure of that appearance
Yeah.
of the room with the time reversal symmetry of the ensemble of all the appearances.
But hang on. So if the measure isn't time reversal symmetric, then somebody says, "Oh, I see. We're building the time reversal asymmetry into the measure."
Yeah, but that's not right. You give me a trajectory. Along this trajectory, almost every point is not time reversal symmetric. But the theory is perfectly time reversal symmetric.
Yeah, no, but this is a really simple logical matter. So the time reversal asymmetry is in the measure.
The measure
measure violates time reversal symmetry.
If I look at the measure on what is p at integer values of q, there's a correlation between p and q in the actual appearances of points along that trajectory.
Good.
There's not in the Liouville.
So the measure explicitly includes a direction of time.
Every trajectory has a direction of time. The dynamics and the Liouville measure don't.
Right. No, we're not using the Liouville measure.
Right.
So the measure we are using has a direction of time built in.
The measure says that given the existence of this room, it is very, very likely that we're in the middle of a big entropy gradient and there's a direction of time. Yes.
No. I know that that's what you wanted to conclude. I want to understand that.
So that's the measure. So I'm saying that what you're looking for is a theory of dynamics in which along every trajectory, it is the case that when this room appears, it had a big bang in the recent past.
That couldn't possibly be just a feature of a dynamical theory. It must be a feature, as you're saying, of a dynamical, because the dynamical theory we're all agreed is time reversal symmetric. For every solution where we're going up this way, there's another solution where we're going down this way. Okay.
We should probably let other people talk,
Okay.
but I'm going to say it again. That is a true statement about the space of trajectories, but along every trajectory, there's an arrow of time almost everywhere. That's the difference.
Jumping to the arrow of time from a cosmological perspective, if you're looking for an asymmetry to find the arrow of time, something natural is just the fact that we live in a small region compared to the big infinite space or very large space that surrounds us. So for example, if you interpret the entropy of the cosmic horizon as ignorance of what lies beyond it, and it's clearly much greater than the entropy of anything interior to it. Would you say that if you have a situation where that is true, you're going to get an arrow of time? Or if you have the space outside the horizon is bigger than the space inside the horizon?
Don't see why that's true. I can think of plenty of conditions in Minkowski space, at least, to get rid of some cosmological words. But in a Minkowski background, there's many localized collections of stuff that do not have an arrow of time, no matter what's going on outside. So I'm not sure. I mean, entropy, there's more than one definition of the word entropy. We're really talking about, for the collection of stuff you have, there is a Boltzmann entropy, and it's much lower than it should be. And I don't think that argument helps you.
So,
Oh, sorry, yeah.
just to sort of
Follow up, yeah.
if we saturated the amount of entropy that's on the cosmic event horizon inside, that's one way of thinking about we'd be in the maximum entropy configuration. There wouldn't be room for any arrow of time inside. There wouldn't be any way for structure to grow. Isn't it suggestive that there is this huge gap between the horizon entropy and the actual entropy? And that seems to follow from having a larger amount of space outside than inside.
I don't think it does follow from that. It could be in equilibrium and still have a A lot of stuff outside.
In the Sitter space or in Minkowski space?
Either one. Well, I don't know what outside means. If it, in any finite volume, I think that could be true. Let's talk afterwards. I'm not sure I understand the problem.
I think I know the answer to this now. But I mean, originally when I asked about sort of motivation for this, part of your response was that, look, it would get some interesting dynamics from this, interesting stuff from the on, then I would itself. I mean, how much of this project depends on the measure stuff working out? I mean, there does seem to be a sort of a general, say, logical suspicion that something special has to come in at some point, whether it be something specialness in the sort of space of trajectories or the wave function of the universe or something, and sort of worries could be re-raised about the specialness of that condition. And you might say, look, that's fine. I've given you sort of more about the world than you knew. This is a nice picture. It's got the simplicity, yada. Or you could say, no, if you find ourselves in that position again, we should go home. Where would you like to be?
Well, I think we should be empiricists. I think we should accept what we eventually come up with as the best theory of the world. So the fact that I would like to find a non-special set of starting points that get me the special condition that I'm in now doesn't give me any guarantee of success in doing that. It might be that the best understanding of the world involves some statement along the lines of it's special, somehow, special initial conditions or whatever.
I mean, so say this doesn't work out. Is the response, look, we shouldn't have gone down this particular route, or we should give up on the philosophical aspirations to explain the specialness?
I don't think it will. I don't think that there's any, in my mind, future outcome of the progress of physics and cosmology that would make me think that what I was doing, that what I am doing now is a mistake. It could be that I'm wrong. Typically, theoretical physicists proposing models are wrong a lot more than right. But I don't think that, I mean, in order for that to happen, it would not be sufficient to just say, well, the universe is special somehow. The necessity of that specialness would have to be obvious, and that is far from true.
So you are sort of, I'd say, you seem most strongly wedded to the idea that the specialness should be explained.
The idea I'm wedded to is that when you see specialness, you should try to explain it. You may or may not succeed.
Right. There are various places one could look to revise a failure, and I was trying to find what would kind of, and it seems like the specialness would be the last thing you'd want to give up explaining. You'd be willing to kind of go and stuff.
I think that in this case, at least, the fact that the specialness, that it is sensible to try to explain the specialness, is helped along by the fact that we know we don't have the full theory of cosmology, right? We don't have the full theory of quantum gravity, what happened to the Big Bang, blah, 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 blah. So we're using that specialness as evidence, right? As a clue towards trying to help come up with a theory of cosmology that fits. If we had a working theory that fit everything except for one little positive specialness, then the motivation would be less. And I will let you go there. Thanks.